Hello everyone, and welcome to the second part of the tutorial for decades of array signal processing, an optimization relaxation technique perspective. My name is Minh Trinh-Hoang, and it has been a great pleasure for me to be one of the co-presenters of this tutorial in OICO today. As Mats has already presented in the first part of this tutorial, the optimal parametric methods enjoy remarkable estimation performances in many cases. However, the computational complexity is high. In order to reduce the computational complexity, in this part of this tutorial, we are going to introduce the concept of approximation relaxation and its application to the optimal parametric methods. We are going to see that many conventional DOA estimators can be reinterpreted as an approximation, relaxation, or both of the original optimal parametric methods. So first, we are going to quickly revise the concept of approximation and relaxation. Then we are going to look more closely into the conventional spectral-based DOA estimators.
After concentration with respect to the nuisance parameters, we can reformulate the optimization problems of the optimal parametric methods in part 1 of this tutorial in the following manner, where we minimize a particular cost function f with respect to the steering matrix A. Note that we have an additional constraint, that the steering matrix A must lie on the steering array manifold AN. The cost function f depends on which criteria we used to match the received signal with our model. Generally, after concentration, the cost function f is non-convex with respect to A. In addition, the feasible set AN on which we are optimizing on is also non-convex. Therefore, generally it requires a high computational complexity to obtain the global minimum of this optimization problem. In order to alleviate this difficulty, we are going to resort on the approximation relaxation techniques to obtain a suboptimal solution of the original problem. As the feasible set is non-convex, we can modify it either by relaxing or restricting to make the optimization problem somewhat easier. Or an alternative approach is to modify the cost function by successively approximating it by some upper bound functions. The relationship of these approaches is summarized in the following. Instead of searching on the original feasible set, we can relax the true steering array manifold AN to a relaxed steering array manifold AN bar. Alternatively, in the approximation method, we replace the original cost function f with a different function f bar, and this new function is easier to minimize. We normally choose the approximated cost function f bar as an upper bound of the true cost function f, as given in the following figure. The reason for this choice is that if we minimize the upper bound function given here by f bar of alpha at the given point alpha k hat, the next iteration point, denoted here by alpha hat of k plus 1, ensures that the original cost function will decrease. And therefore, if we successively perform this upper bound approximation, the solution of the approximated problem will converge to a local minimum or a setup point of the original function. In the relaxation technique, the array manifold AN, denoted here in the black region, is relaxed. We can choose a relaxed set AN bar to be convex, which generally simplifies the process of obtaining a suboptimal solution. The relaxed solution, denoted by A hat relaxed, generally does not lie on the original array manifold. Therefore, at the end we have to perform a projection back to the original array manifold so that we can estimate the DOAs. At this point, we would like to remark that how to choose the relaxed feasible set AN bar depends on the geometry of the sensor array, and sometimes even on the original cost function f of a. Another remark here is that the back projection step here in the second step here does not ensure that we can obtain the original global minimum a hat. Interestingly, in some special cases, like in the extended invariance principle, we can prove that the projected solution is asymptotically optimal. This indicates that we suffer from no estimation loss in the relaxation step while the computational complexity is reduced. Now we will show the application of the approximation relaxation concept to the DOA estimation problem. We can show that many conventional spectral-based DOA estimators can be interpreted as a single-source approximation of the optimal parametric methods. Then, by exploiting a different relaxation technique from the conventional base, now we will show the application of the approximation and relaxation concept to the DOA estimation problem. We can show that many conventional spectral-based DOA estimators can be interpreted as a single-source approximation of the optimal parametric methods. Then, by exploiting a different relaxation technique from the conventional spectral-based DOA estimators, we introduce a novel framework entitled partial relaxation framework. In the single-source approximation, instead of searching for n DOAs at the same time as in the optimal parametric methods, we perform a spectral sweep. At a given direction theta, we compute the cost function f to that direction's small a of theta, but not on the full steering matrix capital A of theta as given in here. This value is called the null spectrum at the given direction. Then we perform a spectral sweep over the discretized field of view. The position where we attain the n deepest local minima are considered to be the estimated DOAs. We can summarize the whole procedure of the spectral sweep in the following shorthand notation, where we find the position of the n deepest local minima of f. The null spectrum that we have here actually has a very nice interpretation. It indicates how well we can fit our received signal under the assumption that there is only one source signal located at the current candidate DOA. The following animation will help us understand this interpretation more in detail. The measured signal at the sensor array in the noiseless case is a linear combination of the steering vectors corresponding to the source signals. At each candidate DOA, denoted by the red marker here or here, we attempt to match our measured signal with the steering vector from that candidate DOA. Note that we do not consider the influence of the remaining source in the model, and therefore the remaining columns of our steering matrix are empty. The null spectrum basically represents the residual error between the measured signal and the reconstructed signal from the single source model. Then we iterate for all DOAs in the field of view. Each candidate direction results in a different residual error. After finishing the spectral sweep, we obtain the null spectrum, which is the residual error for all candidate directions. The estimated DOAs are chosen from the n deepest local minima of the null spectrum. This choice is motivated by the fact that if our candidate DOA coincides with one of the true DOA, the residual error should be smaller than the neighboring directions, and we should see a drop in the residual error around that DOA. With this concept, now we can reinterpret some conventional spectral-based DOA estimators in the literature as the single-source approximation. We first start with one of the earliest DOA estimator, the conventional beamformer. In the beamforming method in general, the received signal at the sensor array X is combined in a linear fashion with each other. The weight of each sensor is gathered in a vector W, which depends on the direction theta. The vector W is called the beamforming vector. Then, at the output of the beamformer, we measure the output power P of theta, which is computed by this expression. We note that the output power of the beamformer depends on both the second-order statistic of the received signal, which in this case here is the covariance matrix, and also the beamforming vector W. In the finite number of snapshot case, we have to replace this expectation operator with the sample mean, and the power obtained after the beamformer is computed as a quadratic expression of the beamforming vector W with the sample covariance matrix R hat. The choice on the beamforming vector W generally depends on the application. If our objective is to maximize the power at a given direction A of theta, then we choose the beamforming vector W to be a scaled version of the steering vector as given by this expression. This choice of the beamforming vector leads to the original derivation of the conventional beamformer, where in each direction we compute the power output as follows. The DOAs are then estimated from the n highest peak of the measured power P hat of the conventional beamformer power. This is an intuitive choice because the directions where most power is located are potentially the true DOAs of the source signals. From a different perspective, we can interpret the conventional beamformer from the approximation relaxation perspective as follows. Let us remind again the expression of the received covariance matrix R. What would happen if we apply the single source approximation on the model of this covariance matrix? Then we would match the sample covariance matrix R hat with one component given here from the steering vector A in a least square manner. Another remark is that we dropped the influence of the noise in our cost function. Then the minimizer sigma s square hat of this optimization problem is indeed the spectrum of the conventional beamformer that we presented in the previous slide. This interpretation confirms again the meaning of the conventional beamformer spectrum, which is the measured power at the sensor array from a given direction theta. One drawback of the conventional beamformer is the limited angular resolution. Even if the noise power is small or the number of snapshots is large, due to the interference of the neighboring source signals, the peaks of the conventional beamformer spectrum do not locate at the exact position of the source signals. In order to suppress the interference of the neighboring source signals, the Capon beamformer, or also known as the minimum variance distortionless response (MVDR) beamformer, tries to minimize the overall power while maintaining a fixed gain at a given direction. This objective implies indirectly the interference suppression from the neighboring sources, and therefore we would expect to have a higher resolution capability than the conventional beamformer. Formulating as an optimization problem, the beamforming vector W is chosen by minimizing a quadratic term with respect to the linear constraint, which is the fixed gain constraint. The solution of this optimization problem is given in closed form by this expression. When we plug this minimizer back to the cost function, we obtain the so-called Capon spectrum, given by 1 divided by a quadratic term with respect to A of theta. The DOAs are then estimated from the n highest peaks of p hat. Due to the implicit suppressions of the interference, the Capon beamformer has a higher resolution capability than the conventional beamformer. Here, we also remark that the Capon beamformer requires the sample covariance matrix, given here in R hat. It has to be invertible. This means that the number of snapshots must be at least as large as the number of sensors. If it is not the case, then we can apply some ad hoc procedure, for example diagonal loading, to make R hat here to be invertible again. Although the expressions of the beamformer spectra that we saw before are quite different, in fact they share a common background. The Capon beamformer or the conventional beamformer can be both considered as a solution of a covariance matching problem. But in these problems, we match the sample covariance matrix R hat with a particular covariance term from a given direction in a least square manner. The only difference is that in the Capon formulation given here, we introduce an artificial constraint which ensures that the residual matrix must be positive semi-definite. From an optimization perspective, this idea of adding an artificial constraint corresponds to a restriction of the feasible set, which makes the optimization problem somewhat easier. We will observe later that by adding this artificial constraint, we can reduce the computational complexity by a great amount without losing much of the DOA estimation performances. Now, we will revise one of the most popular methods, the music estimator. Derived by Schmidt in 1979, the music estimator exploits the orthogonality between the noise subspace and the steering matrix A. A key observation here is that if the source signals are uncorrelated, then UN is orthogonal to the steering vector A of theta if and only if theta coincides with one of the true DOA. This means if we measure the distance between the steering vector A and the sampled noise subspace UN hat, and we take its inverse, this value will be large near a true DOA. And this is actually the original derivation of the music pseudo-spectrum from the perspective of the noise subspace. But what would happen if we look from the signal subspace? Let us remind again the weighted subspace fitting formulation. But here we make one small modification. We drop the weighting matrix W, or in another word, that we set this weighting matrix to be an identity matrix. Then, if we adopt the single source approximation, we have to replace this cost function by this cost function, where we replace the steering matrix A with one particular steering vector A of theta. After some manipulation, actually it is trivial to recognize that the null spectrum of the music estimator given in the expression, which is again the inverse of the pseudo-inverse presented in the previous slide, this null spectrum is actually proportional to this expression. Therefore, we can conclude that the music estimator is in fact a single source approximation of the weighted subspace fitting problem with an identity weighting matrix. Up to now, we see that several popular spectral-based DOA estimators have been reinterpreted as a single source approximation of the corresponding optimal parametric methods. In each direction, we consider only the contribution of one candidate direction while neglecting the remaining sources. Here, one question arises is that, can we also consider the remaining sources while performing a spectral search? Do we also have to resort to another kind of approximation or relaxation? This answer is given next, where we introduce the so-called partial relaxation framework. Similar to the derivation in the single source approximation, let us recall again the optimal parametric methods, where we optimize a particular cost function on the fully structured array manifold AN. The key idea of the partial relaxation framework is that we will relax the original array manifold in a special manner. Each element on the relaxed array manifold retains the geometry of the sensor array in one column. Without loss of generality, we can assume that the structure of the first column here is maintained. On the other hand, the structure of the remaining columns in the steering matrix is relaxed, which is denoted by the matrix B. Now, if we optimize the original cost function f on the relaxed array manifold, we can obtain the DOA information of only one source signal corresponding to the first column of the relaxed steering matrix. In order to obtain all n DOAs, we resort to the method of spectral sweep, similarly to the single source approximation. In each candidate direction, we solve an optimization problem where we search for a relaxed part B of the steering matrix that minimizes the cost function f. Due to this relaxation, the optimization problem is generally easier to solve, and we can obtain a closed form expression for the minimizer of B in some cases. The minimum of this inner optimization problem corresponds to one value of the null spectrum given at the direction A of theta. Then we perform a spectral sweep over the full field of view to search for the n deepest local minima of the null spectrum. These locations are our DOA estimates. We can illustrate the concept of the partial relaxation framework, or PR in short, in the following figures. Say, for a given candidate direction denoted by the red arrow here, we fix the first column of the steering matrix. Then we have to find the relaxed part B such that the cost function is minimized. After performing the optimization, we observe that the minimum is rather high if our candidate DOA is not near one of the true DOAs. Now we move to the next candidate direction, which corresponds to one of the true DOA. Then the minimum of the inner optimization problem is much more smaller than the previous candidate direction. This phenomenon occurs again when our candidate DOA points to one of the true DOAs. We can explain this phenomenon by noting that if the candidate steering vector coincides with one of the true steering vector, that we have it here for examples, then with the B matrix modeling all the remaining n-1 sources, we can achieve a perfect match at a high SNR or high number of snapshots. If, on the other hand, the candidate DOA points to the direction where no source is available, then the n-1 columns of the unstructured part B cannot model the contribution of all n sources. This means that we cannot attain a perfect match when the candidate direction A of theta does not point to the true DOA, and therefore the null spectrum at this direction is large. The computation of the null spectrum is generally more complicated than the single source approximation, because we have to solve an optimization problem in each direction. However, in most cases, we can obtain a closed form solution, which reduces the computational complexity drastically. After performing a spectral sweep, we estimate the DOH from the n deepest local minima of the null spectrum. In the following, we will describe in details how to apply the concept of partial relaxation framework, or PR in short, to the optimal parametric methods presented in this tutorial. So let's start with the deterministic maximum likelihood, where we have to minimize the trace of the product between an orthogonal projection matrix times the sample covariance matrix. When we adopt the PR framework, in this case, we have to decompose the steering matrix A into two components. One structured column A, which is the desired direction that we are considering, and the remaining columns are relaxed in the B matrix. The null spectrum is then computed by minimizing this expression with respect to B. Therefore, we should decompose this cost function into two terms, one depending on B and one not depending on B. This term can be dropped when minimizing with respect to B, and therefore we only have to focus on maximizing this expression, which is the trace of a double projection matrix times the sample covariance matrix. This reformulated optimization problem is still non-convex, but we can obtain a closed form solution for the minimum by applying the eigenvalue decomposition as in this case. We can decompose this double projection matrix as a product of Z times Z Hermitian, where Z is a unitary matrix with a rank smaller than n-1, or at least as large as n-1, and this is orthogonal to A due to the inner orthogonal projection matrix. Using this decomposition, the optimization problem given here can be reformulated in the following form, where we have a quadratic form with respect to Z, and we have two constraints, one linear constraint and one unitary constraint. This reformulated maximization problem admits a closed form solution given by the sum of the n-1 principal eigenvalues of this matrix argument. Or also this matrix arguments, they are the same when we are computing the eigenvalues. Plugging this result back into the original cost function, we obtain a closed form expression for the null spectrum of the PRDMA estimator, which comprises the m minus n plus 1 minor eigenvalues of this matrix argument. The matrix argument is direction dependent, so for each candidate direction in the field of view we have to compute this expression. At this point, we also provide an alternative expression to compute the PRDML null spectrum, and the reason why we introduce this case will be explained later. Up until now, we see that the derivation of the PRDML estimator may seem a little bit complicated, and it seems rather technical. So in the following slide, we will introduce an alternative derivation which utilizes a different concentration order, which may be a little bit easier to follow. In this alternative derivation, we first recall the original least squares problem of the DML estimator as follows. We wish to match our received signal matrix X with our model. Under the partial relaxation framework, the signal model consists of one structured component and the remaining n-1 unstructured components, denoted by B times H. In the PRDML estimator, we have to minimize this expression with respect to B, S, and H. As the matrix B and H contributes in the cost function only as a product, we can combine them into a new variable denoted by E and then concentrate this cost function with respect to S. The original problem then turns into a best rank approximation problem, where the rank constraint comes from the introduction of the new variable E. The solution of this best rank approximation problem in the Frobenius norm sense is given by the sum of the singular values squared, or equivalently the sum of the eigenvalues, similarly to the previous slide. With this derivation, we apply successfully the PR concept to the DML estimator. How about the other optimal parametric methods? By recalling the weighted subspace fitting method, we recognize that it shares a similar structure to the DML estimator, except for the fact that we replace the sample covariance matrix R hat with a weighted version of the signal subspace. This means that we can directly reuse the result of the DML estimator to obtain the null spectrum of the WSF estimator. One key difference in the null spectrum of the PRWSF estimator is that we only need to compute one eigenvalue. From the computational perspective, this is very favorable for us. Another interesting remark is that the music estimator can also be considered as a special case of the PRWSF estimator with an identity weighting matrix. This interesting remark means that the music estimator actually belongs to both class, the single source approximation, and the PR framework. The last optimal parametric method to which we apply the PR framework is the covariance matching problem. Adopting the PR framework here in this case means that we should decompose the true steering matrix A into the structured steering vector A and the unstructured matrix B. The source covariance matrix P is also correspondingly decomposed into four components: sigma S square, rho Hermitian, and then Q. In the first version of the covariance matching PR estimator, we neglect the potential correlation between A and B, or in another word, we will set the rho here to be 0. Next, similar to the Capon beamformer that we presented before, we replace the noise component here with a PSD constraint. Under these approximations, the partially relaxed constraint covariance fitting, or in short PRCCF, is formulated as follows, where we match the sample covariance matrix R hat with the signal component sigma S square A times A Hermitian and the remaining interference components, subject to the constraint that the residual matrix must be positive semi-definite. When we concentrate this cost function with respect to B and Q, we recognize again the best rank approximation problem. And as a result, the null spectrum of the PRCCF estimator is the solution of this optimization problem, where we minimize the sum of the eigenvalues square of some matrix argument, depending on the candidate direction A. Thanks to the PSD constraint, so this constraint given here, this optimization problem with respect to sigma S square admits a closed form minimizer, which is, interestingly, the Capon beamformer that we obtained before. As a result, the null spectrum of the PRCCF estimator is computed as the sum of the squared eigenvalues. The matrix argument on which we compute the eigenvalues is a constant covariant matrix R hat modified by an angle-dependent rank 1 component. This structure of the matrix argument will be later exploited for faster computation of the eigenvalues. But before covering this point, the PRCCF estimator shares one property with the Capon beamformer, namely that the number of snapshots must be at least as large as the number of sensors, or else the sample covariance matrix here is not invertible. We also observe that the inverse of the sample covariance matrix here comes from the PSD constraint that we have it here. This implies that if we drop this constraint, maybe we do not have to enforce the invertibility of the sample covariance matrix anymore. This observation leads us to the second version of the partially relaxed covariance fitting estimator. The PR unconstrained covariance fitting estimator is similar to the constraint version, except for the fact that we neglect the PSD constraint. We can use a similar concentration step as before, and the computation of the null spectrum requires an inner optimization problem in each candidate direction. The solution of the source signal power sigma s square, can no longer be determined in closed form anymore, but we can still use some numerical method to solve for the minimum. One important result at this point is that the eigenvalue function, so lambda k of r hat minus sigma s square a times a Hermitian, is continuously differentiable with respect to sigma s square. This implies that we can use this expression, so the derivative, to compute the local minimum of the cost function with respect to sigma s squared. The expression of the derivative is given here in this expression. Then we can either use the bisection method or the Newton's method to find the local minimum. The last estimator in the family of the partial relaxation framework that I would like to present here is the full covariance fitting. The problem now considers the influence of the desired direction, sigma s squared times a Hermitian, the unstructured interference from the remaining sources, and the noise power denoted here by nu times identity matrix. With this complete formulation, the computation of the null spectrum is rather complicated here, where in each direction we have to solve a one-dimensional optimization problem with respect to sigma s square. Again, we can use the Newton method to compute the null spectrum of the PR-FCF method, so full covariance fitting. Up to now, we have presented a class of novel DOA estimators, the partial relaxation framework. In order to gain more insight into this novel class of DOA estimators, in the following slides we will present a quick overview of the DOA estimators that we have already mentioned in this tutorial and their relationship between them. So, in the first column, we have the optimal parametric methods that have been presented in the first part of this tutorial. Using a different matching criteria, the deterministic maximum likelihood, weighted subspace fitting, and covariance matching estimators are derived. Next, if we restrict the feasible set such that we consider only one source signal during the spectral search, then we come up with a third column here, where we obtain the conventional beamformer, k-point beamformer, and the class of music estimator. Note that we can obtain one DOA estimator from different criteria. For example, the conventional beamformer is the result of applying signal fitting with a single source approximation, or the covariance fitting. In the middle column that we have here, we have the novel partial relaxation framework, where in each candidate direction we consider multiple sources in our cost function, similarly to the multi-dimensional search methods. However, the difference is that to make the problem tractable, we relax the structure of the interfering sources, and the DOAs are estimated similarly to the single source approximation methods. Due to the relaxation, we observe that the eigenvalues play an important role in the computation of the null spectrum of the PR estimators. On the one hand, this relaxation reduces the computational complexity compared with the optimal parametric methods. But on the other hand, the performance of the PR framework degraded significantly if the source signals are correlated. This degradation can be explained by the following case study. Let us assume the noiseless case with two fully coherent source signals. Then the received signals is a matrix of rank 1, given in here. If we apply the PIDML method, then for each candidate direction A of theta, we have to find an unstructured B vector such that this cost function here is minimized. As B is unstructured, we can choose B to be the sum of two original steering vectors given in here, and therefore we can achieve a perfect match for all possible candidate direction. This means that the spectrum is then flat, and we can no longer estimate the DOAs from the local minima of the null spectrum anymore. So, with this example, we know that one disadvantage of the PR framework is in the correlated source signal case. But how about the uncorrelated source signal case? Does the PR framework also perform close to the optima? Before answering this question through the simulation results, let us consider one last aspect of the PR framework, which is the implementation aspect. The null spectrum of the PR estimators, for example, the PRDML given in here, or the PRCCF given in here, requires the computation of the eigenvalues extensively. We also remark that we only need the eigenvalues, but not the eigenvectors. The matrix argument of the eigenvalue also share a common structure, which is a constant Hermitian matrix subtracted by an angle-dependent rank 1 component. Therefore, it would be of great interest if we compute the following core numerical problem given here as efficiently as possible. Without loss of generality, we can assume that the constant Hermitian matrix is a diagonal matrix, and the rank 1 component is denoted here by this term. This problem is also called the eigenvalue decomposition of a rank 1 modification Hermitian matrix. This core numerical problem can be solved efficiently using the rational approximation method, and one implementation has been included in the well-known LabPack library. To further accelerate the computation, we can exploit two additional remarks here. The first remark is that we can reuse the previous eigenvalues for faster computation, because it will converge faster. The second remark is that we can either reformulate the null spectrum such that the number of eigenvalues that we have to compute is as small as possible. For example, in the case of the PRDML estimator, if we know that the number of sources n is almost as equals as n, then we should use the first formulation here. On the other hand, if we know that the number of source n is small, let's say 1 or 2, then the second expression here is more attractive in terms of computational complexity. So now, after considering some technical aspects of the PR framework, in the following we will illustrate the estimation capability of the PR estimators in some simulation setups. In the first simulation setup, we assume a uniform linear array with 5 sensors receiving the uncorrelated source signal from two sources. And the DOAs are located at the angle of 135 degrees and 140 degrees. The number of snapshots t is set to 150. Here in this case, we vary the signal to noise ratio. We also here compare the performance of the PR estimators given here, DML, WSF, CCF, and SCF, to one single source approximation method, namely the music estimator, and one optimal parametric method, the DML estimator. We can see that among the PR estimators, the estimation performances of the covariance fitting base, denoted here by the red markers and the red line, they are very favorable, where they almost coincide with the high computational complexity of the DML estimator. The DML and WSF estimator, in the partial relaxation framework, achieves the Cramer bound at the SNR much lower than the music estimator, while the computational complexity of the PR estimator and the music estimator are in the same order of magnitude. In the next setup, we fix the SNR, but we vary the number of snapshots. Again, we can observe the estimation behaviors similar to the previous setup, where the covariance fitting base DOA estimators can estimate the DOAs with two sources when about 40 snapshots is available, so almost similar to the DML estimator. The PRWSF, PRDML, and music estimator requires much more snapshots to resolve the two sources here in all Monte Carlo trials. So, in this second part of the tutorial, we revise the approximation and relaxation concept, which has been widely known in the optimization context. Then, by applying two special cases of this concept to the optimal parametric methods, we rediscovered several spectral-based DOA estimators in the literature and their relationship between them. In the next part of this tutorial, Marius will present other approximation relaxation techniques that can also be applied to solve the DOA estimation problem.